Hey physics friends, Mr. Collier here, and I've got another sample problem for you with conservation of energy. Here we've got a bouncy ball that's dropped from 2 meters above the ground, and it's going to bounce back up to 1.5 meters above the ground. We want to know its velocity just before the bounce and its velocity just after the bounce. So, one of the key things here is that as it goes from high to low, its potential energy is going to change into kinetic energy. And we are going to assume from the law of conservation of energy that all of the potential energy turns into kinetic energy. So that means that the potential energy at the start is equal to the kinetic energy at the bottom, right? And at the beginning, it was dropped from 2 meters. And so we're going to set up mgh would be our initial scenario, and our kinetic energy would be 1/2 mv squared. Now, one of the realizations in this problem is since the mass is going to be the same, it doesn't actually matter what the mass is when you're setting these two values equal to each other, and so we're going to be able to cancel them out, which is helpful since the problem didn't give us the mass. So now we can rearrange this for v, and v is equal to the square root of 2gh, which is actually a pretty nice simplification. So this h is going to be the height that it was dropped from. So the velocity equals the square root of 2 times 9.8 meters per second squared times the height that we dropped it from, which is 2 meters. That's going to give us a velocity of 6.3 meters per second. Now, the ball bounces, and in that bounce, some of the kinetic energy is not kept as kinetic and potential. It's transferred to other forms of energy. For example, the ball makes a sound, there's a little bit of loss of heat, there's the object deforming when it gets smushed as it bounces. And so after the bounce, it's actually the ball is not going to have all of that energy. Some of that energy is going to go to other forms. And so that's why when a bouncy ball bounces, it doesn't return to its original height. And in B, how fast is it going after the bounce? We're going to actually end up doing the same calculation, right? That the potential energy it has, except now it's at the end, right? After the bounce, is equal to the kinetic energy it has at the bottom just after. And so we're going to do the same thing where mgh is equal to 1/2 mv squared. Our mass is canceled, and we get the velocity is equal to the square root of 2gh, just rearranging that equation. The key difference here now is that this height is our new height, where it only bounces to 1.5 meters. And when you plug in that value, you're going to find that after the bounce, and I'm going to call that the initial velocity after the bounce, is equal to 5.4 meters per second. And so it has, understandably, it's moving slower after the bounce because some of its kinetic energy that it went into the bounce with has been turned into other forms of energy that are not going to help it bounce. That's it from me. Let me know if you have any questions.